Have you ever stopped to wonder why some things in nature seem to, well, only go one way?
Hmm.
Like that hot cup of coffee you just poured, it always cools down in a cooler room, right?
Ways, yeah.
But it never, ever spontaneously heats up on its own by, soaking up warmth from the air around it.
Nope, never see that happen.
Why is the reverse never observed? It seems so obvious, but there's a really deep reason behind it.
It really is.
Okay, so let's unpack this a bit. We're doing a deep dive into the second law of thermodynamics.
Right.
Now, you're probably familiar with the first law. That's the one all about the quantity of energy, how it's conserved, never created or
The
destroyed.
bookkeeping law, basically.
Okay.
Energy in equals energy out.
Exactly. But the second law adds these, well, crucial, almost eye-opening dimensions. It dictates the direction processes actually occur in.
Which way things go.
And it reveals the very quality of that energy. It's not all the same.
And what's truly fascinating here, I think, is how the second law fills this huge gap left by the first law.
How so?
Well, the first law, as powerful as it is, doesn't tell us if a process can actually happen in the real world.
Right. Like the coffee heating itself up. The first law wouldn't forbid that, technically.
Exactly. Energy would still be conserved. But the second law just says no. It completely remedies that inadequacy.
Ah,
It's the principle that helps us sort out which processes are physically possible, not just theoretically imaginable. And it sets fundamental limits on what we can actually achieve.
so a process has to obey both.
Absolutely.
Yeah.
It cannot occur unless it satisfies both the first and the second laws of thermodynamics. No exceptions.
And this deep dive, hopefully, will reveal those unseen rules, the ones governing everything from, your daily coffee
Mm-hmm.
to the massive power plants that light up our cities. It gives you a kind of shortcut, maybe, to understanding the real essence of energy and how it behaves.
Let's get into it.
Okay, let's start with those everyday examples where the first law alone just doesn't cut it. We mentioned the hot coffee cooling off.
Right. Never gets hotter spontaneously from the cooler air. It's definitely a one-way street.
Or think about heating a room with, say, an electric resistor. Easy, right? Electrical energy turns into heat pretty readily.
Yeah, happens all the time.
But you never see the reverse, do you? You never see heat from the room air spontaneously generating electricity in those wires.
No, that would be quite something. But no.
And one more picture. A weight falling, turning a paddle wheel that stirs up some water, making the water warmer.
Okay, yeah, converting potential energy to internal energy via friction.
Right. But you'd never see the reverse. The warm water somehow transferring heat back to the paddle wheel and making the weight rise up again.
Definitely not. These are really clear illustrations that all processes proceed in a certain direction and not in the reverse direction.
So the first law might allow these reverse scenarios in terms of energy balance,
It would, yes. Energy conserved either way.
but the second law just flat out forbids them.
Absolutely forbids it. It's the direction compass.
So it's really non-negotiable then. You can conserve all the energy you want, but if it's not going in the direction the second law permits.
It just won't happen. Simple as that.
And here's where I think it gets really insightful. The second law also asserts that energy has quality, not just quantity.
Ah, yes. This is a huge concept.
While the first law is only counting the joules, the second law introduces this, well, revolutionary idea that not all energy is equally useful.
Exactly. And this concept of energy quality, it isn't just some academic detail. It's fundamental for engineers.
How does that play out practically?
Well, it means you don't just count the total energy in a system. You have to consider its potential to do useful work. High-temperature heat, for instance, has higher quality than the same amount of heat at a lower temperature.
Because you can get more work out of it.
Precisely. More of that high-temperature energy can be converted to work. So preserving the quality of energy becomes a major concern. It changes how you design everything from power plants to industrial processes. You start thinking about minimizing the degradation of energy quality, not just preventing energy loss.
So waste heat isn't just lost energy, it's energy that's lost its usefulness, its quality.
You got it. It's been degraded to a lower quality state.
Okay. So to understand how we do manage to convert heat into useful work, we need a concept first, right? This thermal energy reservoir.
Yes, exactly. Think of it as a hypothetical, idealized body with an incredibly large thermal energy capacity,
Meaning?
meaning it can supply or absorb a finite amount of heat without really changing its own temperature,
Well,
like a giant ocean for heat.
okay. So real-world examples would be.
Well, large bodies of water, oceans, big lakes, rivers, they often behave very much like thermal reservoirs. The atmosphere is another classic one.
Right. Or even industrial furnaces, if they're large enough and kept at a constant temperature.
Exactly. If they can supply a lot of heat without their temperature dropping significantly, they act as a high-temperature reservoir or a source.
And the place where heat gets dumped, like the river or the air, that's the sink.
That's the sink, yeah, the low-temperature reservoir that absorbs the heat. And this source sink idea is critical for understanding heat engines. It's also why things like thermal pollution are an issue dumping waste heat into rivers, using them as sinks.
Okay, so heat naturally flows from hot to cold, from source to sink. How do we tap into that flow to get work done, like powering cars or generating electricity?
That's where heat engines come in. They're the devices designed specifically for this purpose.
And they all work on the same basic principle.
Pretty much, yeah. They all have universal characteristics.
Hmm.
First, they receive heat, let's call it kin, or QH, from a high-temperature source.
Okay.
Second, they convert part of that heat into useful work, like turning a shaft. Let's call that win-out.
Only part.
Only part. That's key. Third, they must reject the remaining energy as waste heat quote, or QL, to a low-temperature sink.
They have to. No choice.
No choice. And fourth, they operate on a cycle. They return to their initial state to repeat the process over and over.
Right. Like an engine piston going up and down.
Exactly.
Yeah.
And the classic example, the one that really illustrates this, is the steam power plant.
Okay, walk us through that briefly.
Sure. You have a boiler. That's where heat, QH, comes in from burning fuel, turning water into high-pressure steam.
High temperature, high quality energy.
Right. Then that steam expands through a turbine, making it spin. That's your work output, weaned out.
Got it.
After the turbine, the now lower pressure, lower temperature steam goes into a condenser. Here, it rejects waste heat, QL, to a cooling source, like river water or cooling towers, turning back into liquid water.
So that's the heat dumped to the sink.
That's the essential heat dump. And finally, a pump pushes the liquid water back up to the high pressure of the boiler, requiring a small work input, and the cycle starts again.
Boiler, turbine, condenser, pump. Operates in a cycle, takes heat high, gives work, rejects heat low. Checks all the boxes.
Perfectly fits the definition of a heat engine.
And how do we measure how well these engines do their job? There's an efficiency measure, right?
Yes, thermal efficiency, usually written as ATAT 3
And that's basically what you get out versus what you put in.
Exactly. It's the network output divided by the total heat input. So 1 out divided by QH.
Or you could think of it as how much heat you didn't waste.
Right. Since the network is just the heat in minus the heat out, weighing out QH, QL, the efficiency is also 1 minus the ratio of heat out to heat in, 1 QL, QH.
Okay, so higher efficiency means less waste heat for the same work output.
Correct. And here's what's really fascinating and maybe a bit disappointing.
No.
Thermal efficiency is always less than 1 or less than 100%.
Always. Why?
Because that waste heat, QL, it's never 0. You always have to reject some heat to the low temperature sink to complete the cycle.
Even in a perfect frictionless engine.
Even then, it's not about practical imperfections. It's fundamental. Think about the best power plants we have today, the really advanced combined gas-steam cycle ones.
Yeah. What do they manage?
They top out at around 60% efficiency, maybe a tiny bit more in some cases.
60%. That means 40% of the energy from the fuel is just dumped.
Dumped as waste heat, yes. Nearly half the energy input is rejected to the environment.
Wow. That seems like a huge amount of waste. So the obvious question is, can we save that quote? Can we somehow design an engine that doesn't need to reject heat?
That's the dream, right? But the answer, according to the second law, is a very firm no.
Why not? Why can't the cycle just stop before rejecting heat?
Because you wouldn't be able to get the working fluid back to its initial state to start the cycle over again without cooling it down. And you can't cool something down by transferring heat to something hotter.
Right. You need that low temperature sink. You can't say cool steam from 90 degrees Celsius down to 30 degrees Celsius by trying to transfer its heat to a reservoir that's already at 100 degrees Celsius.
Exactly. Heat just doesn't flow uphill like that spontaneously. So rejecting heat to a colder sink is absolutely necessary to close the cycle.
So even under ideal conditions, quote, cannot be 0.
Cannot be 0. And this fundamental limitation leads us directly to one of the most important formal statements of the second law.
Which is?
The Kelvin-Planck statement.
Yeah.
Named after Lord Kelvin and Max Planck.
Okay, what does it say?
It says, It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work.
So you can't just have a source, get work out, and have no sink.
Precisely. You need at least two reservoirs, a source and a sink, to operate a heat engine cycle. A 100% efficient heat engine, which would only need one reservoir, is impossible.
And this isn't because of friction or leaky seals or anything practical.
No, this is a fundamental limit. It applies to all heat engines, perfect, ideal ones, and the real ones we actually build. It's a law of nature.
Okay. That sets a pretty hard limit on things. Now, what about when we actually want to move heat the wrong way? From cold to hot?
Yes. Defying the natural flow.
That's where refrigerators and heat pumps come in, right?
Exactly. These devices do perform that seemingly unnatural act of transferring heat from a colder medium to a warmer one.
But they can't do it for free.
Definitely not. They are also cyclic devices. But unlike heat engines which produce work, refrigerators and heat pumps require an external work input to operate. That's the cost of moving heat uphill, thermodynamically speaking.
Like the compressor in your fridge using electricity.
Precisely. That electric motor drives the compressor, which does the work needed to run the refrigeration cycle, typically a vapor compression cycle.
So what's the main difference between a fridge and a heat pump, then? They seem similar.
They operate on the same cycle, fundamentally, but their objective is different.
How so?
A refrigerator's main goal is to remove heat, let's call it QL, heat from the low temp space, from the cold space, to keep your food cold.
Right. The desired output is cooling.
Whereas the heat pump's objective is to supply heat, QH heat to the high temp space, to a warm space like heating your house in winter.
Even if it's taking that heat from the cold outside air?
Yes. It pumps heat from the cold outdoors into your warmer house. The desired output is heating.
So for these devices, we don't talk about efficiency in the same way.
No, we use a different term, the coefficient of performance, or COP.
Okay, COP. How's that defined?
It's always defined as the desired output divided by the required input.
So for a refrigerator?
The desired output is the heat removed from the cold space, QL. The required input is the network you put in, Wheaton. So QPR equal QL Wheaton.
And for a heat pump?
The desired output is the heat delivered to the hot space, QH. The input is still Wheaton, so COPHP equals QH Wheaton.
Got it. Desired effect over work cost. And you said earlier QH is always QL plus Wheaton for these devices, right? From energy conservation.
Correct. The heat rejected to the hot side is the heat absorbed from the cold side plus the work done.
So does that mean COPHP is always related to COPR?
Yes, it is. Since QH, QL plus Wheaton, if you divide everything by Wheaton, you get QH Wheaton, you get QH Wheaton plus 1, so CPHP, COPR plus 1. Always for the same operating conditions.
Ah, interesting. So the heat pump's COP is always exactly 1 greater than the refrigerator's COP operating between the same two temperatures.
That's right. And here's another key difference from thermal efficiency. COP can be, and usually is, greater than 1.
Really? How? Isn't that like getting more out than you put in?
Not quite.
Yeah.
Remember, the input is work, but the output is heat transfer. You're not creating energy, you're just moving it using the work input. So a heat pump with a COP of, say, 3 means for every 1 unit of electrical work you put in, it delivers 3 units of heat to your house.
Where do the other 2 units come from?
They're extracted from the cold reservoir, the outside air, or the ground, depending on the type of heat pump. It's moving existing heat, not creating it.
Okay, that makes more sense. Can you give a quick example?
Sure. Let's say you have a household fridge with a COPR of 1.2. If it removes heat from inside at a rate of 60 kilojoules per minute, then the power it needs, Wheaton, is 60 divided by 1.2, which is 50 kilojoules per minute. And the heat it rejects to your kitchen, QH, is QL plus 1/8. So 60 plus 50 equals 110 kilojoules per minute. That's the warm air you feel behind it.
Got it. And a heat pump example.
Okay, imagine a house losing heat at a rate of 80,000 kilojoules per hour on a cold day. If you have a heat pump with a QPHP of 2.5, the power input needed, 1/8, is 80,000 divided by 2.5, which is 32,000 kilojoules per hour.
So you only pay for 32,000 kilojoules of electricity.
Right, but you get 80,000 kilojoules of heat delivered to the house. The other 48,000 kilojoules are being pumped in from the cold outdoors. That's why they can be very efficient for heating.
That's pretty clever. So just like Kelvin-Planck stated something impossible for heat engines, is there a similar statement for refrigerators and heat pumps?
Yes, there is. It's called the Clausius statement, after Rudolf Clausius, another giant of thermodynamics.
And it says?
It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body.
Meaning you can't just have heat flow from cold to hot spontaneously without any other effect.
Exactly. You need that work input. A refrigerator that could run without being plugged in, just making things colder by dumping heat into the warmer room with no external help, is impossible, according to the Clausius statement.
Okay. And are these two statements, Kelvin-Planck and Clausius, related?
They are entirely equivalent. They're just two different ways of expressing the same fundamental limitation imposed by the second law.
How do we know they're equivalent?
You can actually show, logically, that if you could violate one statement, you could build a device that violates the other one too. For instance, if you had a device violating Clausius, moving heat from cold to hot with no work input,
Yeah.
you could combine it with a regular heat engine. The net effect would be a device that takes heat from a single reservoir and produces work, violating Kelvin-Planck.
Ah, I see. So violating one implies violating the other.
Exactly. They stand or fall together.
Yeah.
They're both expressions of that fundamental one-way nature described by the second law.
Which is why these laws are so robust. And they also explain why people's dreams of, say, perpetual motion machines never pan out.
Precisely. Speaking of violations, let's touch on those perpetual motion machines again briefly.
Okay.
We have two main kinds people talk about. A PMM1, or perpetual motion machine of the first kind, is a device that would violate the first law.
By creating energy from nothing.
Yes, getting more energy out than you put in. We know that's impossible because energy is conserved.
Right. And the second kind?
A PMM2, perpetual motion machine of the second kind, is one that violates the second law.
How would it do that?
Typically, it's imagined as a heat engine that's 100% efficient. It takes heat from a single source and converts it all into work with no waste heat rejected.
Which is exactly what the Kelvin-Planck statement says is impossible.
Exactly. So a PMM2 is impossible due to the second law.
And you know, it's kind of amazing how many people have tried to build these things over the centuries.
Oh, countless attempts. Some incredibly elaborate. There was even this one, the hydropneumatic pulsating vacuum engine.
Seriously?
Yeah, patented by J.W. Kelly, claimed to run forever. Of course, it didn't work.
Because none of them ever have.
Never. The U.S. Patent Office actually got so tired of them, they stopped even considering applications for perpetual motion machines way back in 1918.
Because they just fundamentally violate the laws of physics.
Fundamentally, you just can't get something for nothing, violating the first law, or get perfectly efficient conversion of heat to work, violating the second law.
Okay. So these laws set hard limits. Now, you mentioned earlier this idea of ideal processes. This relates to something called reversibility, right?
Yes, exactly. This is a really crucial concept for understanding the limits of efficiency. We talk about reversible processes.
What does that mean exactly?
A reversible process is an idealized theoretical process that, once it's happened, can be reversed in such a way that both the system and its surroundings are returned to their exact initial states, leaving absolutely no trace that the process ever occurred.
No trace at all, like perfect backtracking.
Perfect backtracking. It's a purely theoretical benchmark.
Because in reality...
In reality, all processes are irreversible.
Why? What makes them irreversible?
Things we call irreversibilities. These are the factors that prevent a process from being perfectly reversible.
Like what?
Well, friction is a big one. When there's friction, some energy is always dissipated as heat, warming up the interacting surfaces. You can't just reverse the motion and recover that dissipated energy perfectly to cool things back down.
Right. Friction always generates some waste heat.
Exactly.
Yeah.
Another one is unrestrained expansion, like a gas suddenly expanding into a vacuum. It does no work because there's nothing to push against. You can't just reverse that spontaneously. You'd have to do work to compress the gas back.
Okay.
And perhaps the most common one is heat transfer across a finite temperature difference. Whenever heat flows from something hot to something colder, that's an irreversible process. To reverse it, you'd need heat to flow from cold to hot, which, as Clausius told us, requires external work.
So friction, sudden expansion, heat transfer between different temperatures, these always happen in the real world.
Always. That's why all real processes are irreversible. They leave some change behind in the universe.
So if these reversible processes are impossible, just theoretical fictions, why do we even bother talking about them? What's the practical point?
That's a fair question. They're incredibly useful because they serve as the ultimate benchmark. They represent the absolute best-case scenario.
The theoretical limit.
Exactly. Reversible processes tell us the maximum possible work output you could ever hope to get from a work-producing device, like a heat engine, operating between certain conditions.
And the minimum input for work-consuming devices.
And the absolute minimum work input required for a work-consuming device, like a refrigerator or heat pump. They define the pinnacle of thermodynamic performance. Real processes can only approach this limit. They can never exceed it.
So we compare actual engine performance to the performance of an imaginary, perfect, reversible engine.
Precisely. It tells us how much room for improvement there might be.
Okay. And is there a specific famous reversible cycle?
Yes, the most famous one is the Carnot cycle, conceived by Sadi Carnot back in the 1820s.
Carnot. Okay, what's special about it?
It's a theoretical cycle composed entirely of 4 reversible processes operating between 2 thermal reservoirs at constant temperatures, TH high and TL low.
What are the 4 processes?
2 of them are isothermal, meaning they happen at a constant temperature. One is an isothermal expansion at TH, where heat QH is absorbed, and the other is an isothermal compression at TL, where heat QL is rejected.
Okay, constant temperature heat in, constant temperature heat out.
Right. And the other 2 processes are adiabatic, meaning no heat is transferred during them. One is an adiabatic expansion, where the temperature drops from TH to TL, and the other is an adiabatic compression, where the temperature rises back from TL to TH.
So 2 heat transfers at constant temp, 2 processes with no heat transfer, and all 4 are perfectly reversible.
That's the Carnot cycle. And because it's made entirely of reversible processes, it represents the most efficient cycle possible, operating between those 2 specific temperatures, TH and TL.
The absolute maximum efficiency.
Yes. And this leads to what are known as the Carnot principles.
Okay, what are they?
There are 2 main ones. First, the efficiency of any irreversible real-world heat engine operating between 2 reservoirs is always less than the efficiency of a reversible, like Carnot, heat engine operating between the same 2 reservoirs.
Makes sense. The ideal is always better than the real.
Right. And the second principle is maybe even more striking. All reversible heat engines operating between the same 2 temperature reservoirs have the same efficiency.
Wait, all of them? Regardless of how they're built or what fluid they use?
Exactly. As long as they are reversible and operate between the same TH and TL, their efficiency will be identical. It depends only on the temperatures, not the details of the engine.
That's profound. So efficiency has this universal limit based only on temperature.
It does. And this second Carnot principle actually provided the breakthrough needed to establish a truly fundamental temperature scale. Because the efficiency of a reversible engine depends only on the reservoir temperatures, Lord Kelvin realized you could define temperature in terms of heat transfer ratios in a reversible engine, independent of the properties of any particular substance like mercury or alcohol used in conventional thermometers.
Ah, so you define temperature by how efficiently heat can be converted to work.
Essentially, yes. This led to the thermodynamic temperature scale, which we now call the Kelvin scale. On this scale, the ratio of heat transfers in a reversible engine, QHQL, is defined to be equal to the ratio of the absolute temperatures of the reservoirs, THTL.
So QHQL for reversible engine equals THTL, where T is absolute temperature in Kelvin.
Precisely. And they fixed the scale by assigning a specific value, 273.16 Kelvin, to the triple point of water, where ice, liquid water, and water vapor coexist in equilibrium.
Giving us a temperature scale based on fundamental thermodynamics, not just the expansion of mercury.
Exactly, a truly absolute scale.
Okay, so if the efficiency of a reversible engine is Rev equals 1 QLQH, and for a reversible engine, QLQH equals TLTH.
Then you get the famous Carnot efficiency. Tth Rev equals 1 TLTH.
And this formula gives the maximum possible efficiency for any heat engine operating between the absolute temperatures TH and TL.
That is correct. It's the theoretical ceiling. No heat engine, no matter how perfectly designed, can ever exceed this efficiency.
So if you have a power plant taking steam at, say, 600 degrees C, which is about 873 K, and rejecting heat to a river at 20 degrees, about 293 K,
Yep.
The maximum possible efficiency is 293,873, which is about 0.665 or 66.5%.
Exactly. So that 60% achieved by the best real-world plants is actually getting impressively close to the theoretical Carnot limit for those temperatures.
Wow. And this equation, Rev equals 1 TLTH, it really drives home that point about energy quality, doesn't it?
Absolutely. It shows clear as day that the higher the temperature of the source, TH, the closer the TLTH ratio gets to 0, and the higher the maximum possible efficiency.
So higher temperature heat is more valuable, higher quality, because a larger fraction of it can be converted into work.
Precisely. Energy available at high temperatures has a higher work potential. That's why engineers are always trying to push operating temperatures higher in power plants,
Yeah.
within material limits, of course.
It's like that analogy you mentioned, the quality versus quantity of friends. Having lots doesn't mean they're useful. Having high temperature energy means it can be useful for work.
It's a good analogy. It captures the essence. When we talk about wasting energy, we're very often talking about irreversibilities that degrade the quality of energy, letting high temperature heat leak away, or mix with lower temperature surroundings without extracting the work it could have done. We're turning high quality energy into low quality energy, even if the total amount stays the same.
So it's not just about conserving energy, but conserving its quality, its usefulness.
That's a huge part of what the second law teaches us about managing energy resources effectively.
Okay. And does this Carnot ideal apply to refrigerators and heat pumps too? Is there a maximum possible COP?
Yes, absolutely. If you imagine running a Carnot heat engine cycle in reverse, it becomes a Carnot refrigerator or heat pump cycle.
And it would be the most efficient possible refrigeration or heat pump cycle between TL and TH.
Exactly. It would require the minimum possible work input to move a certain amount of heat.
So what are the formulas for the maximum reversible COPs?
Using the same relationship, QHQL equals THTL for a reversible cycle and the definitions of COP, you find that COPR rev equals 1 THTL1, which simplifies THTL.
Okay, COPR rev equals THTL.
And since QPHP equals COPR plus 1, the maximum COP for a heat pump is QOPHP rev equals THTL.
So again, the best possible performance depends only on the absolute temperatures you're operating between.
Only on the temperatures. And notice that as the temperature difference, THTL, gets smaller, the theoretical COPs get larger. It's easier to pump heat across the small temperature gap.
Right, which is why heat pumps work best in milder climates.
Generally, yes. And these Carnot COP formulas show the upper limit. Real refrigerators and heat pumps will always have lower COPs due to irreversibilities like friction and heat transfer across finite temperature differences in their heat exchangers.
But modern appliances are getting better, right? You hear about much higher efficiency fridges now than, say, 20 years ago.
Oh, absolutely. There have been significant improvements. Better insulation reduces unwanted heat gain. More efficient motors and compressors reduce the work input needed. Engineers have designed larger coil surface areas for the condenser and evaporator, which reduces the temperature differences needed for heat transfer, making the cycle closer to reversible.
And even simple things like better door seals.
Yes. Better door seals reduce air infiltration, which is another source of irreversibility and load on the fridge. All these things add up to bring the actual COP closer to that theoretical Carnot limit.
And we can help too, right? Like keeping the coils clean.
Definitely. Dust on the condenser, coils at the back or bottom of your fridge acts like insulation, making it harder to reject heat. Cleaning them lets the fridge run more efficiently using limited energy. Checking door seals for leaks also helps. Little things matter.
Okay, so let's try to wrap this up. We've covered a lot of ground.
We have. It's a deep topic.
So, to summarize, the second law of thermodynamics. It's really this profound principle that does a few key things. It dictates the inherent direction of processes.
Right. Things only go one way spontaneously. Coffee cools, it doesn't heat up.
It sets the ultimate performance limits for all devices that convert energy or move heat, like engines, fridges, heat pumps.
Through concepts like the Carnot efficiency and Carnot COP,
Yeah.
it tells us the absolute best we can ever do.
And maybe most importantly, it highlights this crucial concept of energy quality, not just quantity.
Yeah, that high temperature energy is more useful, more capable of doing work than low temperature energy.
So the big takeaway is just conserving the amount of energy, like the first law tells us to, isn't the whole story.
Not at all. We also have to think about preserving its usefulness, its quality. We need to minimize those irreversible processes that degrade energy into less useful forms.
It's a really powerful framework for understanding what efficiency truly means, and maybe why some tasks like getting work from low-grade heat are just fundamentally harder than others.
It explains so much about how the world works, from the smallest scale to the largest power plants.
So maybe here's a final thought for you, the listener. Next time you hear discussions about energy consumption or energy waste, try thinking beyond just the amount of energy involved. Ask about its quality. How useful is it? And think about the direction the second law is inevitably pushing that energy towards a less useful, more dispersed state. What other aspects of your daily life, maybe things you haven't considered, might be subtly governed by these fundamental one-way rules of energy?